Thank you, Molly. Good morning, everybody. So I have the pleasure of introducing our first speaker today, which is Sandaruwan. So Sandaruwan graduated from the University of Moratuwa. I apologise if I'm pronouncing it terribly, from Sri Lanka in 2016, and was one of the youngest lecturers to be recruited at the Institute of Technology there, which is very impressive. And I do want to know how old you were when that happened at the end, but I'll hand over to you. So take it away.
Oh, thank you so much, Nikita. Just give me one moment to share the slide. And when I was recruited, I just passed out like 26 or 7 years old. That's for Sri Lanka, it's a very early age. All right, hope you can see my slides. Right. Okay, thank you so much, and very good morning to you everyone present here. So when it comes to my research topic, the research study I'm doing for my PhD is a development of shape memory polymer composite-based deployable components for modular habitats. And my principal supervisor is Associate Professor Jayantha Parachi. When it comes to this presentation, I will separate it into 5 categories mainly. So introduction and the shape memory polymer synthesis and optimization for my application. And then using that shape memory polymer, we in short form, I will call it SMP. Using that one to develop on the fabricate the shape memory polymer composite, which is in short form SMPC. And then I'll be testing that for the durability, and then shape memory polymer components design and fabrication for the end use. So when it comes to the introduction part, basically I will be introducing what is shape memory polymer. Sometimes you might already know some of it. And so basically when it comes to shape memory polymers, it's just like other polymers. There are thermoset polymers, thermoplastic polymers, and only added advantage it have is the shape memory property, which usually when we fabricate the polymer, that will be the final shape or the permanent shape of it. And usually we can use external stimuli such as heat, it can be magnetism, there are pH, different chemicals, and electricity. Using different stimuli, we can program it to take another shape, and we can use the same stimuli to take it to its original shape. So basically, that's the shape memory properties that shape memory polymer shows. So this is the unique ability, but most of the shape memory polymers, just like any other polymers, they have inadequate mechanical properties when it comes to the final applications, as we do on CFM. And when it comes to polymers, we use reinforced fillers, reinforcing fibers to enhance its mechanical properties. So mostly, in most cases, like most cases for shape memory polymers, they are usually enhance their properties by adding fibers and fillers. We will be doing that in this study as well. When it comes to my research, and there are a number of applications when it comes to shape memory polymers and their composites, including aerospace, space, automotive, textile, biomedical, and soft robotics and civil structures. When it comes to my research area, it will be like a combination of two, which is civil structures and space applications. So I'll be making structures for space, in simply put. So when it comes to space applications so far in the previous literatures, there are scientists have done making hinges and deployable solar arrays and deployable substrate and reflectors and booms, things like that. And some of them has even gone to the trials in space, where mostly lower Earth orbit. So in this case, my research is to make not the little application like hinges and deployable solars, but this will be making structures that can be deployed and make hole in another place in the space. It can be lunar environment, it can be the space or the LEO environment. Well, basic idea or the research hypothesis of this research is to create and manufacture the component on Earth. For example, as I shown in this slide, one of them is like a 1/8 of a hemisphere, and then there's a cylindrical part. The idea behind is if we can uh, make it flat and make this cylinder flat sheet, and so it is very easy for us to keep them in a payload fairing of a rocket with saving space, saving the area inside it, the volume inside it. And once we take it into the place we need to create the structure, we can recover it back to its original shape and put them together. There are various mechanisms for that. Um, and put them back. So in here, I have shown some pressure vessels kind of structures in here. So when it comes to my research specifically, we have decided to go not all of this, but to go with a very bit of a complex shape, which is the hemispherical shape. And I will try to make this 1/8 part of this hemispherical shape or the shell part and program it and take it to its original shape back and complete the hemispherical shape. Now, for this is why we need a shape memory polymer suitable for this, and to develop the shape memory polymer composite, and we go through so many troubles to make it happen. Now, so as the second section of this presentation is that shape memory polymer synthesis and the optimization. So first, we need to find a shape memory polymer for that. And basically, when we going to select the shape memory polymer for that, we have to consider the high temperature properties, because most of the time in the space it can go up to in the Leo environment, it can go up to more than 130 170 degrees even, and in the lunar environment it can go up to 125 27 at maximum. The minimum temperatures are also like that, it can go minus 170 somewhere around that as well. And so because of that, we have to check for the shape memory polymers capable of withstanding that kind of temperatures. And also we had to go through a huge literatures, a number of literatures to do a durability studies, which shape memory polymers are capable of doing that from the existing ones. And also it should have excellent shape memory properties to recover back into original shape as well. And so we have done that, and I will explain it later in the slides. And secondly, I will explaining how the shape memory polymer is synthesized. And there we need to think about the chemical ratios. What are the chemicals we are going to use? And then what is the curing cycle? How do you going to cure that? And then sample fabrication. So when it comes to this research, sample fabrication was a major task, because almost all the things were done at higher temperatures, like somewhere around 100 degrees. Um, Lastly, in shape memory property optimization, once the shape memory polymer is synthesized, we have to check what is the best chemical combination that have best properties thermomechanically, mechanically, and when it comes to the shape memory properties, which combination has the best properties. So we had to check that as well. Well, when it come to the first thing, the shape memory polymer, the durability study, so we have gone through multiple literatures, and so when it comes to that, we have gone through different exposures, different durability test compared to, regarding temperature, different temperatures, creep, aging, thermal cycles, and shape memory cycles, and also when it comes to radiation and irradiation, that means it can be my electromagnetic radiation like UV, gamma, and also irradiation from the charged particles like atomic oxygen, mostly in the Leo environment. And Leo mean lower Earth orbit, if you missed the slide. And also exposure to electrons and protons. So by going through so much literature, we have come through few shape memory polymers, polyimide-based shape memory polymers, epoxy-based shape memory polymers, and cyanide ester-based shape memory polymers. So from these, after having a look through and comparing through these materials, we decided to go with cyanide ester-based shape memory polymers. Now, when it comes to that, there comes the polymer synthesis part. And for this, we used bisphenol A cyanide ester. And as a modifier, shape memory property modifier, we use oligomers such as polyethylene glycol. We use different types of polyethylene glycols because there are so many variations. So we use 600 molecular weights, 1000, 2000, and 4000. Because even there was a small amount of literature that used these two, there were no exact chemical mention in the literatures. This is what we use to make this particular SMP. And sometimes even those shape memory polymers, they didn't have the properties we need for our application. So we have to innovate a new shape memory polymer using different chemical synthesis, like chemical ratios for that. And when it comes to bisphenol A cyanide ester is a thermoset polymer that doesn't need any hardener. It's like a one component thermoset polymer that can cure by itself. And here we, like, during the synthesizing process, we made over 20 types of samples, like different with different chemical ratios, and we tested each of them for their thermomechanical properties using DMA. That is the main concern we had when it come to this mixture of these two components to enhance their thermomechanical stability. So I will explain it in the next slide. So the main issue we faced was when we combine these two materials to get the shape memory polymer shape memory effect. The shape memory effect was there, but when it comes to the stability at higher temperatures that we can measure from the storage modulus when we're doing a DMA test, mostly the shape memory polymers that had lower molecular weights, polyethylene glycol had that property. And even so, in this storage modulus graph, if as you can see, this is like we use the same stoichiometric ratio 21:1. That is 21 mean cyanide ester molecules, and 1 mean the polyethylene glycol. That ratio. And here you can see how they have performed with the same stoichiometric ratio. So you can see in here 600 polyethylene glycol 600 and 1000 has performed particularly well. Um, so we chose these different two variations to go forward with and see which one is the best. And we did so many mechanical tests, shape memory recovery and fixity test, and few other high temperature tests as well. And both of them perform really well because when you have a higher molecular weight, basically that will increase the toughness of the material, basically toughness of the cyanide ester. But when we have lower molecular weight, polyethylene glycol, it not better like the polyethylene glycol 1000. But when it comes to the thermal stability, thermomechanical stability at higher temperature, polyethylene glycol 600, that particular ratios we chose performed well. So in that case, we went forward with polyethylene glycol 600 for the as the modifier for our shape memory polymer for the next steps. So as you can see here, we went forward with a 9:1 ratio. So the basic idea behind this is we have developed a model as well. I didn't put that in that slide in here. When it comes to using this ratio, we can have a stable thermomechanical properties at 130. But we can have different ratios. So we can have stable thermomechanical properties even at 200 degrees. But this one, we aim for the basically the lunar environment and the lower orbit environment. And also it have activation and program. It can be activated and programmed at 170 degrees as well. This is basically where we optimize the shape memory polymer. Now, after that, then the next step was to fabricate the shape memory polymer composite. And for this, we need to select materials apart from the shape memory polymer. For this, we use, apart from these two components, we use graphene nanoplatelets. So we add 0.6% to the weight ratio. The main idea behind that was to increase the thermal conductivity of the shape memory polymer composite. And because it doesn't have any carbon fiber, we are using glass fiber. So that's the fourth component of this composite. We decided to use the glass fiber because from our previous research done by our other group members previously, We found that like mostly when it comes to the shape memory programming and recovery, uh, mostly the flexibility the glass fibers have actually has an added advantage for these particular movements rather than much stiffer carbon fiber and even basalt fiber. And that is one of the reason we went with glass fiber. And second thing, we have to think of what is the fiber layout configuration of this composite layout. So in order to decide that, we went for three different fiber layout configuration. So one is all the composites has 6 layers of glass fiber. Only variation was their directions. So one had a T, I have mentioned the T configuration here. T mean it have 0 90 degree composite, sorry, glass fiber layer, 6 layers in there. And the second one is the X, which have minus 45, 45, plus 45 glass fiber layers, 6 layers. And the last one was like a hybrid one, which is we mentioned as TX, that have 3 0 90 and 3 minus 45 plus 45 in like a sandwich layer. So when it come to the 0 90 or the T configuration, it's like a strong mesh. And when it come to the X configuration, it looks like it mostly had a scissor like moment, which have that flexibility. And basically the hybrid mesh or the TX mesh had a like kind of a hybrid or in middle properties in that case. And we tested them for different properties, such as mostly we were thinking of what will be the mechanical properties after and before and after the shape memory programming and recovering. So that's something we need to actually have a look, because that is important when it comes to the end usage of when it comes to the application level. And after that, we also optimize some of their properties, and decided to select one of them for our end application. So as you can see here is the shape recovery behavior of the shape memory polymer composite, different fiber layer configuration. Here I will like simply explain. So if you can see B9 GT, that is B9 means the bisphenol to cyanide, sorry, polyethylene glycol ratio, and then G mean the graphene nanoplatelets are there, and T and XTX are the configurations. So here you can see the poorest performance by when it comes to the shape recovery is GT. So the T configuration does not assist much when it comes to the shape recovery and programming. I will explain it in another slide here. Give me 1 minute for that. And also we check before and after mechanical properties. So I have just presented here only the ultimate stress before and after. As you can see, I have put another two at the end. This is N and G. These are the neat shape memory polymer, and the last one is the graphene filler included shape memory polymer. And you can see the other different fiber layers here as well. Now, so as you can see here, um, the most percentage of drop of the properties can be seen in the T configuration, and less amount of drop can be seen in the X configuration because of this scissor-like movement. And in middle, there's TX. So now we had to decide what is the shape memory polymer fiber layer, composite fiber layer we are going to go forward with. So in here, we had to decide what to do. And as you can see, the reasons behind the uh, poor performance by T configuration, as you can see in image A, when we program it to 90 degrees angle, you can see the fiber slippage is there, like destroying the matrix and everything at one part. So this is basically the reason for it to perform poorly. Compared to that, the X um, configuration did very well. However, we have to decide to which way to go, because what we are making is not a directional component. It have forces to every direction, because as a hemisphere, it has the hoop stresses and axial stresses, and mostly on the surface, it has stresses in everywhere. So when it comes to these three configuration, to TX, that will be the mainly the best performing, overall best performing shape memory polymer composite. So we decided to go forward with that particular fiber layer configuration. Now, after deciding that, the next step was to test it for durability. So when it comes to durability, we have done three, and we are going to do another two test. And first one was the vacuum thermal aging. We did it in P11 in Tumba, and we kept samples for 4 weeks at 140 degrees inside the vacuum oven
Why?
to see. Sorry. Okay, so we kept it for 4 weeks there, and I will present you the result in the next few slides. Now, also we did atomic oxygen exposure test in atomic oxygen interaction facility at ANU in Canberra, and we did it for two types of shape memory polymer composites, with one in graphene with graphene nanoplatelets, the other one without the graphene nanoplatelets, and see whether there's any difference. And lastly, we did a high temperature stability test, testing their tensile and fracture properties at 100 degrees and 120 and 140 degrees. Apart from that, I have done a creep test, and we are going to do a cryogenic temperature aging test next week. Hopefully, those results will be added into this durability test as well. And when it comes to the results of the vacuum thermal aging, we found out like there's minor chemical structure changes after carefully going through the FTIR results. So basically, it is related to the thermal degradation of polyethylene glycol. Usually, when it comes to the cyanide test structure, it have cyclometric structure where it have trypsine and different circular and stable structures, which is very strong. And the weakest bond or the crosslink was the polyethylene glycol crosslink, which have degraded over time. However, this is kind of good results in my opinion, because this will, when we into the application level, this will happen eventually once our end use of the applications is done. That means the shape recovery has been done. That means it is increasing its properties in strength wise after during the aging, because of the less and less amount of polyethylene glycol 600 crosslinks over the time. And when it comes to the atomic oxygen exposure, so as I told you, we did for two types of shape memory polymer composite with and without graphene nanoplatelets. As you can see in the left side, you can see the graphene included one, and the right side you can see the neat or the without graphene nanoplatelets. So here, after going through the CM scans and image analysis as well, we could found that the shape memory polymer composite, which has graphene nanoplatelet inside, has less effect from the atomic oxygen erosion. The erosion was common for both materials, but less amount of erosion could be found from the graphene nanoplatelet. That makes it like much better candidate for a application, because it has less degradation when it comes to the atomic oxygen exposure, which is make it good candidate for LEO applications and structures. Thirdly, I'm not going to give much of the results here, because it might take a lot of time to explain them. But when it comes to high temperature stability, with the increase in temperature, the tensile properties came down a little bit, from around 50%. And even though it has kept a good amount of properties at 140 degrees even, for us to develop this and design this application. And finally, when it comes to the shape memory polymer component fabrication, so this is the current stage of the research now. And we have designed and we got fabricated this aluminum mold for the vacuum assisted infusion, like not resin infusion, vacuum assisted molding. So we use this mold, and using different fiber layups, as in T and X fiber layups, as a sandwich method, and we use them and pour the molten uh, shape memory polymer uh, chemicals in there and spread it, and then vacuum assisted. We use vacuum assisted, and then we made these particular components, and right now we have made more than 10 components, and in the process to complete the hemispherical shape and do the recovery and shape memory programming tests. So hopefully in maybe next 2-3 weeks we will be able to do that. Yeah, finally, as our future works, that is one of the things we're going to do, the test the shape memory properties of the components, and then components will be assembly to show the prototype. And also we're gonna test the cryogenic temperature aging next week, and we'll be doing the thermal conductivity, air permeability, and dielectric constant test for depending on the time we have, and for the it's much be better for the final application. And also numerical modeling for the bond strength. I'm currently doing it now. Numerical modeling for the bond strength of the pressurized hemispherical shell, and also for the shape programming. So these are some of the references I use. Most of them were the one we published already. And yeah, that's basically it. Thank you so much for listening to the presentation. And if you have any questions, yeah, now's the time. Thank you.